Welcome everyone. Today we're going to be looking into some of the MongoDB internals. Let me see if this works. It works. And I have to ask the first question here. Who knows about MongoDB? Right. Who never tried MongoDB? Get out. No, kidding. You're okay. Just sit tight. But if you don't know about MongoDB or never tried it before, and you're just wondering what it is, it's actually a very good talk to get along with, or get to understand a little bit about how does a MongoDB or a database in actual works. So we're actually going to be looking into some things which is kind of a hot fix. So we're going to be looking into things that we are working on, and we're going to be changing them a little bit in the end. So we're going to be actually coding a little bit of C++ at the end. Anyone here a good C++ developer? All right, not that many people, so I can screw around, no one will notice. That's fine. So we're going to be looking into an overview of MongoDB, what it is probably not. And we're going to be looking into the architecture of MongoDB, what are the different components that make for a database. We're going to be looking into the data model, we're going to be looking into the persistency and storage engines, we're going to be looking into the APIs, things that you guys as developers will be using to use MongoDB and to build your cool applications. And we're also going to be looking at the end, as I said in the beginning, a little bit of how it's actually been built and actually the code that's behind the magic around MongoDB. First and foremost, these are my contact details. I don't always dress on a bow tie. Sometimes I do, but only on special occasions. But anyway, if you want to reach out, Twitter, email, anyway, I'll be more than happy to answer any of your questions. So, a little bit of an introduction. So, for the ones who know about MongoDB, you probably know these three things. It's a general purpose, open source, document-oriented database. Document-oriented because we store, in contrast to our relational, typical default databases, which we generally store things into rows and tables, we store things into documents. Documents are very things that we're going to be looking into in more detail, but they're probably very similar or very known to you as objects. If you are an object-oriented programming developer, you probably are, or probably been touching some of it. You've probably been using those kinds of objects in documents or data structures that are very, very similar to you. The idea behind MongoDB, and this is not always working, is to give you a full-featured database. We are not interested in making sure that we are good for this particular niche kind of use cases. We want to make sure that you as a developer, you can build wherever you want, whenever you want, with the tools that you know to do any kind of use case at any time. So we have an analytical workload that can be processed by either our aggregation framework or our MapReduce engine. You can express rich queries using our MongoDB query language. You can do all sorts of different applications using geospatial capabilities or even aggregated data anytime that you like. It's with a simple programming model that you just call a library and you execute code on it. Today, scalability is a major factor, factor for choosing a database. And something that is always going to be living in a small box, or you need to grow the box every time you want to scale out or scale your system, is probably not the way to go forward these days. We want to build massive applications that are spread across multiple continents, and we want to have all the data of the world. And you smile when your user gets in and gives you more data, because this is what makes your applications richer, more engaging, and much more interesting. So we need a database that also allows you to scale in a horizontal fashion. And obviously, if you don't have something that can survive failure, which basically is high availability systems, you probably cannot rely too much on that technology, or you will be scrubbing a lot of heavy lifting or waking up late in the evenings to make sure that the box doesn't fail, or if once it fails, you have someone touching the button and saying, hey, there is a new node again, it's all recovered, uptime. So we want to make sure that you can build reliable systems on top of replica sets, which are a high availability system. And if someone doesn't know what high availability is or what it's for for failover. And the best definition of failover would be something like this, where you keep on rolling. No matter how many tricks you have under your sleeves, no matter... And I have a meeting. This always happens, right? So no matter how many tricks you have in your sleeves, you don't want to fail ever. So that's high failover. That's why replica sets are there. There's lots of people that like us. There's more than 10 million downloads. There's a lot of people taking courses online for free on our online education platform. I definitely recommend you all to, if you want to learn a little bit more about MongoDB under the context that you're expert on, in your Java language or your Python language or whatever language you like. There's a multitude of courses out there to help you get started and get learning and improve your skills. There's obviously a lot of conferences and so on that we like to participate on. Okay, enough of the setting the table. Let's get into what the architecture is looking like. If you want to have a highlight of what MongoDB is, you can think about it in this way. It's pretty much a layered application where you have on the sides administrative procedures like security and logging and auditing and all that. You have on top an application, can be your application, can be an IoT platform, can be a customer representation data, a CRM system, a catalog management system, you name it, you build it, you take care of it. We offer you an API, which is a library, most sure you are using some of our libraries already if you're using MongoDB. It's basically an idiomatic way to interact and call MongoDB. You don't need to learn another language like SQL. You just need to call a specific library that you say, I want to do insert this or update that or find this particular document. We give you that. That's our MongoDB query language and the APIs that deliver, the drivers. Internally, we have a data model. This is how we represent data. I'm going to be looking into exactly how we represent data in MongoDB. And then that data, guess what? It's a database, so it needs to be persisted from time to time. Otherwise, you lose it. So this is why the definition of a database, you are actually going to store data into disk. We use a multitude of different storage engines which allow you to adjust whatever your needs are in terms of workload to better match the performance you are expecting. So let's get started by the underlying layer, the persistency layer. Now in MongoDB we have currently on our current release 3.0 version only two different storage engines, which are Wiretiger and mmapv1. Currently, mmapv1 is still the default, but on 3.2 we're going to have even more storage engines. We're going to have an in-memory storage engine. It's going to be beta just to make sure that you are aware of how it works, and if it fails you can't blame us. We're going to have an encrypted file system, and Wiretiger will become the new default. The good thing about the storage layer at the end is that we have a storage layer or a pluggable persistency layer API, meaning that you can build your own storage engine if you want to. Guys at Facebook, I don't know if you know Parse and Facebook. Anyone knows Facebook around here? Small startup, no, I've never heard of it. So they have their own storage engine called RocksDB. They call it RocksMongo, which is a cool name, and it's quite a nice way to store data as well. They made this port out of LevelDB, a project from Google. It converted it to something called Rocks, and now they use it under MongoDB because they see a lot of value in the expressivity of the language and they want to store it using their own thing. That's fine. You can do the same exercise yourself. You can pick up whatever storage engine you decide to build if you think you are building a very good storage engine. Very few people in the world actually do that. So don't be ashamed if you're not doing that. But you can actually expand our pluggable storage engine API and build your own if you want to. Then we're going to have our data layer. This is where we are going to do a lot of things like storing documents, creating indexes, creating databases, creating objects, and creating collections. We kind of name things a little bit differently around the data layer because we actually store data in a different format. Generally, you understand data are presented in rows and tables, and then linking them all together with references and foreign keys. Well, we think that you can store data in a completely different fashion using documents and the BSON structure. BSON stands for binary serialization object notation, which is pretty much the same thing as JSON, but in a binary format, with a couple of enhancements that we're going to be looking to in a few seconds. And then obviously we have the storage, the MongoDB core language and the derived APIs. And here is that, well, the part that you know. I want to use some particular, in this case, the best language in the world, which is Python, as you all know. You want to find or insert a document. You could just express something like, I want the DB, I want to call a collection, and I want to insert a certain set of a dictionary or sets of dictionaries and update them and insert them and all sorts of different things. All of this language, all of this maneuver between data of your application and the database is handled by this layer over here. But don't forget about one thing. We are talking about distributable databases to begin with. So we don't think just in terms of architectures, something isolated runs in a machine. Obviously it needs to. It needs to have hosts somewhere. But then we have a full distributed system that has replica sets from one side to give us that skateboarding and keep on doing our tricks all over the place without falling down. But also the availability and scalability distribution that a horizontal scalability shard environment will give you out of the box. You don't need to change your code. You don't need to change the way you interact with your application to actually scale out your system. And this is the beauty of using something like Mongo. Let's go into detail. So we have different storage engines. We actually even have a storage engine API that allows you to expand even further. So why do we need that? Well, if you think about the vast amount of different applications that we build, they probably have different requirements in terms of how they use the persistency layer. If you think about an IoT system, and probably everyone knows IoT by these days because it's a big buzzword that we are constantly hearing all around the interwebs, you'll see that there's millions of sensors everywhere. Everyone has a mobile phone these days, and they are constantly pinging back home some kind of information. Where you are, what temperature is around you, who your contacts are. There's plenty of different sensors right now in our fridges, in our smart meters at home, in power cables, trying to get as much information on real time or not, or just accumulative data across what is going on in the system and having somewhere where we can represent that or store it and query it from time to time. But if we think just on that use case, you'll see that there's a huge amount of difference between the workloads. You have a very write-intensive application out there, and you'll read it from time to time in an aggregated fashion, probably to chart some dashboard saying, hey, this house over here is having this consumption, that other house over there is having that other consumption, and see graphs of it. But if you're thinking about a chat application like Slack or some of those IM kind of applications, you'll see a 50-50 kind of workload. A lot of people write, a lot of people read as well. And if you think about catalog management tools like, I don't know, Amazon Shop, not web services, but the actual shop that started selling books, you know, can sell you panties and stuff. There's a lot of reads, a huge amount of reads all over the place, everyone reading that information. And a few writes every time you want to check out some shopping cart or you want to actually buy something from the actual website, then is when you're going to write. So these different workloads need different ways of actually dealing with the data at the end. And this is why we built the Storage Engine API that allows you to actually build and plug in different storage engines, keeping your application, keeping exactly the same code that you built, but adjusting the underlying persistency layer to what actually your application is going to require. There are a few. We have Wiretiger. Wiretiger's focus is going to be the new default on 3.2, which is about to get released. It's very, very good storage engine built for write-intensive applications. If you have a massive write-intensive application that wants to distribute and consume all the data in the world, but write a lot, and have a nice considerable amount of reads as well, you can use Wiretiger for doing that. 100K inserts per second, no problem, on a single node. And you can scale out if you want more. We have our good old mmap v1. mmap v1 is thought for systems that basically interact a lot with your RAM, and we don't care about RAM management or memory management. We will leave that all to the operating system. It's based on memory map files. I don't know if anyone here not familiar or familiar with memory map files? Well, memory map files is basically the diagram over there, which you have files in disk. They will be mapped into virtual memory with addresses pointing to those positions in disk. If you try to access some data in your disk, they will be allocated those pages in RAM, and they will stick there till the LRU, the least recently used page algorithm in your OS, going to flush them out. And this is going to be based on usage. If you have a data set that you know is going to be of X amount of size, and you have nothing else running in your system, this is a practical, very, very efficient way of dealing with that. On the other hand, if you write a lot, since he has a lot of locking and to control the accesses to those pages, you'll see that there are going to be a little bit more delay there when compared with Wiretiger. And there's obviously reasons why you want to have an encrypted file system. This is going to be based on Wiretiger, so it's probably going to have the same kind of performance associated with encrypted, with the overhead of encrypting everything from end to end. Meaning that you're just not going to be storing or interchanging data in a ciphered way with SSL and TLS and all that stuff, but you're actually going to be storing in disk using a ACE256 encryption key that you can manage with the MKIP or something like KMIP that you can manage with any system that you already have in place for your big enterprise architecture. This is generally very, very needed from financial services or even very sensitive data where you don't want to take the risk of being hacked and going to be accessing your data, and it's going to be sitting there open to everyone to read it. And obviously, well, in-memory is a thing, but it's also reality. There's many, many, many different use cases out there. Probably some of you are building up some of them that require low or none durability of data. You just want the data to be live and kicking, and you want to capture it as fast as you can and get as fast as it can getting out of it with a lot of queries. Think about it, the tick data that you want to correlate all the exposure of a particular operation to certain types of combinations. You don't want to wait for that thing to go to disk. You want to keep the data in your memory, have a bunch of memory to work with it, and just operate with it. Lots of writes, lots of reads, all of that concurrently. This we tend to make, well, I think we have reached it in some tests, but the idea here is not to have 100K inserts per second, it's probably to have 1 million inserts per second per core of your CPU. So this is kind of the throughput that we really want to achieve with such systems. When we deal with data model, we deal with a different kind of terminology. Things are not as they used to be. When we're talking about relational systems, we talk about database, tables, joins, and foreign keys, and rows, and so on. In MongoDB, we talk about database will always going to be a database, that's fine. A table is going to be a collection. The definition of a table is that you define a structure, while in a collection, you don't define absolutely nothing. You just tell the system, hey, this is a collection. There's going to be a set of documents here. No matter what shape of them, you can just group them together. And this is what MongoDB does. You do not need to impose a structure to your documents. Every single document inside a single collection can be of different shapes, colors, structure, you name it. We don't have joins. We don't have yet joins. We have something very similar to that, but you can always get that with embedding and linking documents in between collections. And obviously, indexes are always going to be indexes, and the rows will be called documents. Multi-level, multi-dimensional data structures that represent the data that you are maneuvering. The graphical representation or analogy is that once you have a couple of different tables, linking them each other by the reference or the foreign key, in MongoDB you're probably going to have a single document having all the inner subdocuments representing those relations to begin with. There's different data structure elements to it. It's a rich data structure, so you don't going to be losing any of that precision of data typing, for example. You're always going to have your floats, you're always going to have your reals, you're always going to have your strings, your integers, and so on. So this is not just JSON per se. You're actually going to have rich data types and structures that you can represent your data clearly and effectively. And there are a couple of benefits around dealing with data in a document fashion. Mostly about the naturality and reducing impedance between what you program and what you actually store. The data that you're storing is the data that you're using, and you should model according with that. It's faster for you, everything is collocated, embedded, making sure that you have that usage in mind and not so much concerned about how is this going to be allocating space in my disk. We want to optimize the usage of data, not so much the persistence of that. And obviously, I was mentioning, you can have dynamic schemas. If your application changes from time to time, you say, well, I want to group this set of documents in the same logical union, which is going to be a collection. And they will vary, and they will vary a lot. Think about shapes, or think about, different attributes that you can define to a certain entity that sometimes are very, very hard to model because they vary little or vary a lot, and you still want to find them all together or group them all together. Well, in MongoDB you can use that just in a dynamic scheme approach. Certain documents will have certain fields, other documents will have other fields. But the good thing about this is it's all defined in BSON. I was mentioning before, it's a binary JSON serialization notation. It allows you to have all the rich data type and data sets, and it's the language that we speak internally. So every time you talk to MongoDB, you're actually sending us some BSON, and we are sending you back BSON. Under the covers, and to extract you from dealing with actually the code typing and the formatting and serialization to BSON, we'll give you a driver that does that heavy lifting for you. And in BSON you have numerous data types, from null value to max key, min key, double, long, timestamp, you name it. You probably can do any kind of programming attributes or any kind of data type that you're already using in your Java language or in your Python or in your JavaScript with that type of serialization and data typing. All right, so how does the query engine actually works? You might have this diagram in mind. So I have my super cool application in blue, and I'm going to send some data to MongoDB and see what happens. Well, the first thing it's going to be doing is making sure that what it's receiving is a valid BSON structure. It will do the parsing of that command. Everything in MongoDB that you send us is going to be defined as a command. That command will have a set of instructions, and we're going to be validating those set of instructions are correct. We are also going to be doing a document validation on 3.2 that I'm going to be talking to you guys and showing to you guys in a few seconds. But the first thing that we will, and there it is. So in 3.2, you will be able to define a preset of rules that we will going to be validating against your documents. So if you say that a particular collection will always have a name field, and that name field needs to be of string type, and needs to be within this enum of values, we can validate that from now on. So it will give you a much more stronger harm, validating that even though you have a lot of flexibility in your schema, you actually can impose certain rules on the server side to avoid, not you guys are always doing the right thing, but your colleagues, the ones that, on the 20% and think they are 60%, those guys that not all the time know exactly what they're doing, they will be restricted by the schema validation on the server. Okay, so you send a query, package with an operation, can be an insert, can be a find, can be aggregation work, whatever you say it is. And we're going to be looking to what exactly that command is. So we're going to be looking for DML instructions. Is it a creation of an index? Is it a creation of a table? Is it a creation of a database? What is it? If it's none of that, we're going to be looking to the set of operations that will change data. If it's inserting a document, or if it's updating a document, or if it's deleting a document, we'll be checking that, and then we're going to be applying those changes accordingly in the database, calling that document model I mentioned before. And if it's not, if it's a query, a normal operation, well, the first thing you're going to be doing is call the query analyzer to check, hey, this query just got here. Which kind of query engine or which kind of query path should I be using to actually deliver back the results? Basically, calculating all the statistics to make sure it analyzes correctly the path, basically using the index that's more appropriate for that particular collection. There's a lot of different CRUD operations. You can create, remove, delete, update, all of those things. Those are defined by those operators up there. It's a find, a get more. Those are always going to be together. Every time you do a find, what you do is open a cursor and get a batch of results. And when you exhaust the batch of results on the API, you do, hey, give me more, please, if there's any more. Then there's an operation kill cursor to just disconnect a connection. You can insert, you can update, you can delete, all sorts of different applications, all sorts of the set of commands that you are mostly used to do in your normal database operations. There's lots of different, for example, parameters for just one single find. The find is not just defining a query in a BSON structure. You can actually do, hey, max scan X amount of documents before you decide which query path to actually use. Tell me that I just want a single batch, or I want to limit, skip, filter the projection of the documents. I don't want all the fields in the documents, I just want a set of them. All of these things are things that the driver will actually hide from you. You don't need to worry about it, but this is actually, let's say, platform that you're being using every time you use our API. And there's a rich query around it. There's plenty of different types of operations and types of queries that you can do. You can do by field, you can use a regular expression. You can even say, hey, just give me everything that matches a particular city and then count it. All of these operational API, these instructions, you are also very accustomed to do using a select star from whatever. Here, you don't need to do it. You just call a function in your library. Same thing goes for write operations. You can write on a single field, you can write multiple fields, you can use arrays, you can use embed documents, you can do all sorts of different transformations using the query engine to do exactly that kind of set of operations. And obviously, one thing that differentiates MongoDB from a set of the other NoSQL technologies as well is the ability to create any kind of secondary index. If you have a query that goes for more than just the primary key, what will happen to that query? Or let's say in the other way, if you have a query that doesn't go at all from your primary key or for your key value store, what happens? Simple, you just need to go through all the elements of the collection in this case, and you're going to need to analyze one by one if their internal structure actually matches what you want. If you're an index, you're probably going to be 1,000 times faster just because you already have a pre-established structure that tells you exactly where the documents are. Another cool feature that's coming on 3.2 is partial indexes. The ability that you will have to tell, hey, just index documents that match this set of expression. Let's say I want to create an index on name, but I only want names of documents that have a particular name that have age bigger than 18. Just to find, that all my users need to be above a certain age. Otherwise, I don't know what we're building. I'll leave it to your imagination what we're building. But let's say we want to, I don't know, only find, using a particular index, only the ones which are above 18 years old. The index is on the field name, but the decision by I'm going to index this document on this particular index or not is based on a completely different arbitrary field. Why is that? Why is that relevant? The smaller your indexes are, the faster your queries are. And if you know that you are always going to be doing a combination of those two values, great. You'll be using an index only for the things that you're actually going to be looking to. And obviously, examples of client APIs, you can do it in Java, you can do it in Ruby, you can do it in Python, and they all look very look-alike, and they all look like the same. The good thing about it is that we focus on making sure that we use your idiomatic characteristics, the sugar syntax of your language. You shouldn't learn a new language. You should just need to express the queries in hash maps in Java, for example. You can do it. or having dictionaries in MongoDB, in Python, you can do it, or even hash map in Ruby as well. Up to you. You know your language, you are experts at that language, you know how to build all your unit tests, the best way is serialize and unserialize, whatever you want to do, we just tag along and give you a driver for that particular language. The only relevant thing to understand here is that our client APIs, they will talk a language, and I was mentioning, MongoDB doesn't really know Java, or doesn't really know Python, unfortunately. It's built in C++, and internally, it just operates with commands. And commands, as I was mentioning, they are all BSON. So BSON is a language that actually MongoDB learns and talks. So the only thing that the driver needs to do, and needs to do well, is actually serialize all of your requests, all your API requests that you do to the system, and put that in a nice BSON command, send it over, and deal with the response. That's all it needs to do. It's very simple. We have several different drivers out there. I would say that covers 99% of all enterprise or any decent projects out there. Well, not decent if you're using some kind of abstract or exotic language. It's probably very decent, but with good support, with large communities behind it, that are interested in actually using it for some nice purposes, let's say, or mainstream purposes. You also have integrations with all sorts of different frameworks that go from Hibernate to Spring to Angular to the Django. All of those are kind of covered. If you have a background on BI, or if your job is to build reports for other people to do decisions on the business, and you have data in MongoDB you want to extrapolate or use it in your best interest, you'll probably going to need a BI connector. And with 3.2, it has a dedicated BI connector that will connect all of the different BI tools without going for specific hacks, which currently the integration exists, but it's not native. With this BI connector, it will definitely be native, using datagrams infrastructure to actually make sure that you can graph whatever you have in mind to the data that you are storing in MongoDB. And there's lots of different tooling, let's say, or the aggregation framework that we provide for analytical purposes is very, very rich. It's so rich that it allows you to extract any kind of aggregated result, projection, sum, whatever you have, giving the flexibility of structure that you might have in your documents. So that's the time we're going to be looking to C++, because there's nothing better than looking to C++ at 5:48 in the evening with a lot of tired eyes. So, as I was mentioning to you guys, this is the source code of MongoDB. You can find it on GitHub, MongoDB GitHub, you'll find it. The baseline structure that we have is that you have the serialization of BSON, a lot of code for doing that. There's the underlying client management. This is where we authenticate your requests, make sure that the BSON structure that you're collecting is correct, making sure that validate if it's a DML, a write operation, or a query. We do all that in this particular package over here. We do all the crypto part for the encryption part over here. We have all the instructions for the database, like, hey, this is basically the data model itself, authentication, making sure that we have the stats, the sorter, the pipeline for the aggregation framework, the indexes, the geospatial capabilities, all of that there. And at the end, we're going to have something like, that I really like to show you, like the pipeline. Aggregation framework is very, very neat. Works in the pipeline, you can express an instruction as a grep, cat, AWK, whatever you want. In the same kind of format, the pipeline of instructions, you can do transformations over data as they fly in, as you get them. So one of the things that I really like to do, and I've done it ahead because compiling the source code of Mongo takes a while. It's C++, it's not Java that you just change a line and you just in time compilation and you have it. But I created here a very simple instruction in the pipeline, in the projects framework. So it's basically an operator that I built myself. This is the expression.h. I don't know if you guys can see that well up there. This is where I'm going to, if you're not familiar with C++, I warn you, not pleasant. You have an H file, which is basically a header where you're going to define structures, functions that can be publicly available for other parts of your code. This is also where you're going to do all the imperative naming conventions saying this particular function receives these particular attributes with these different target types, for example. And this all needs to match between the .h, whatever you have, .h, and the .cpp. What I built here was just basically a expression dev eternity. I can assure you it's not on the code or on the master code on GitHub. And the only thing that I'm going to say is, well, I have expression arity, and this is templating for the ones that know about C++. The good thing about templating in C++. And we're going to define a fixed arity kind of function that will have a dev trinity itself and will take only one argument. With that one argument, I'm going to have two functions, one that's going to be named evaluate internal and one that gets up name. Everyone with me? In expression C++, what we do, and this is very, very simple, is, well, I have my dev trinity operator here. Then I'm going to say that evaluate internal gets the variables, checks the operands, basically will check the fields I'm going to be transforming, and will apply a transformation. And the applying transformation I'm going to be doing here is very simple. I'm going to switch the value. Whatever value comes, can be an array, can be a subdocument, can be a string, by dev trinity. Basically, you're going to be changing the, it's very stupid, it's going to be changing the value, whatever document we have, to dev trinity, period. And then we're going to also need to register the actual operator itself, which is called $dev trinity. If you look into other expressions like week or year or truncate or to upper, these are all operators that we're going to be using from the aggregation framework itself. They will do transformations over the data that is incoming. To better exemplify what we actually do, I have here my MongoDB 3.2.rc3. As you can see, I have these members. This is basically our meetup pages member list. I've used the meetup API to populate all this collection. It's a nice, handy JSON format, so we can use it very quickly. Where we have a set of fields, we have an underscore ID, status, city, photo, and so on. But we have here something called name. And there it is. Okay? So what I'm going to do is aggregate and call not dev trinity to upper. And as you can see, it puts all the names into upper. So it's capital K's all around. Okay? So this works. And what I've proposed to do is to do exactly the same thing, but instead of calling the to upper, sorry, you can't see that well, dev trinity, again. See, this is the new command that I'm creating over here. Right? So it's called dev trinity. Everyone with me? To bullshit you not, if you send some operator that is not in the source code, it will not run, as you can see here. But if instead of pointing to this particular document, I use already predefined binary that I'm using here, which is this Mongo over here. And I have to fast find grep or ps. Yes, my idea. You can see here that I'm using this DB path, which I don't know where it is. Doesn't really matter. I'm just going to be creating a dir folder or a db folder here. Make dir, and I'm going to in this DB folder, export my DB, which is called Meetup, and my collection, which is members, just to have exactly the same data. Here we are, okay? I'm going to launch the previous data set, so I'm going to use this predefined, precompiled binary, which should have our currently made up new operator. Okay, I'm running it. Now I'm just going to, and I'm over time, I know that. And I'm going to go to my sandbox, Eternity. Very quickly, I have my DB here. I'm going to import my data folder, collection members, DB meetup, data is in data. Anyway, MongoDB. Okay, I'm going to use the other example. I'm going to connect to that particular port where my existing folder is on 44.
142.
There we go. Thank you. As you can see here, it's a completely different binary because it has a completely different binary built. And hopefully, if I have any data over here, let me just check that out. Yes, I have. Use test, show collections. I have a db.a.find. We'll see that we have here a name, which you probably know, Jose Mourinho, and I can aggregate on that and call dev-ternity. And it runs but doesn't do any result. Oh, sorry. Here we go. We're going to project. Anyway, it should work. Hey, it's not giving me an error anymore. So that's yes, round table. The pressure of demoing makes us do something very, very amazing. So this is just to show you. Apart my very bad skills at actually making the demos work, but that if you want to expand a open source project like MongoDB using your super skills of C++, or just like me coding whatever the hell is in the rest of the code, it's very easy. We invite you to go into download the 3.2, find the bugs. There's a contest around to get the bugs. Whoever gets the most bugs or more important bugs will get a nice prize. I can guarantee you that. Never stop learning. If there's any good advice I can ever give you is that we have this whole set of different videos out there that are designed to make you experts for real. Not like the ones that come here and do talks on MongoDB and make a mess with the demos. Not those. You actually have very good material out there. Give it a look. If you are looking for a job and you have super high skills of whatever, as you can see, I'm not that skilled myself, and I work for Mongo. If you want to join the team in all these sectors, you are more than welcome. If you use this referral, I'll get money for it, so it's nice. And if you have any other questions, you can use any of these channels. Do we have questions? One question.
I have a question. Unfortunately, I'm one of the few guys sitting here who have not an experience with MongoDB in production. But anyway, you said that the MongoDB works fine with Spring, with Hibernate, which are like back-end stuff, and with Angular, which is clearly front-end stuff. So I kind of understand how you can run a MongoDB on a server, and thus Hibernate can work with it. How does Angular work with it? Does that mean that the database is in the client side, or?
So the question is, what the heck are you talking about, Norberto? Well, you can tell me that a front-end library actually can talk to the database. Is that even suitable? So there are, especially for real-time, and do you know a project called Meteor? If you don't know a project called Meteor, give it a look. It will run client-side MongoDB queries for you. But that's not where the whole Angular thing comes along. The Angular thing comes along with something called the meme stack. The meme stack is a stack by which you can program your applications just using JavaScript. And as you probably know, Angular is a part. It's the A of the meme part. Basically, we allow you to do calls to the database from JavaScript whenever you want, from whatever you want. If you want to do it from the client side, I do not recommend you to do that, but you can still do that. And there are libraries that allow you to connect through that very, very easily. Meteor, for example, also allows you to express queries in an Angular context that are similar to MongoDB. Actually, we use a cache local, which is a library called minimongo, that will time to time synchronize with actual backends. You think you're talking to a MongoDB, you're not, you're just talking to a cache, and that cache will synchronize all the data. It is awesome to actually build real-time, very, very interactive applications with Meteor. Give it a look, it's superb. I'll be around for more questions, and beers, obviously. So come and grab me a beer or buy me a beer. I'm more than happy to do any of those. Thank you.